Okay, we will come back again. So, moreover, the charging current may cause overheating of intersheath, especially in long cables, right. So, this charging current also will be responsible for your what you call heating of that intersheath, right, overheating. So, in view of these practical difficulties, neither of this method of grading is used in practice. So, in reality these methods are not used. Whenever necessary, oil filled and gas filled cables are used. So, these are the things for cable. Now, further thing will come later. Now, come another example, example 2. It is given that find the most economical conductor diameter for single core cable to be used on 33 kV 3 phase system if the RMS value of maximum stress is not to exceed 35 kV per centimeter. Also find the radial thickness of insulation. This is the problem, right. So, you have to find out that most economical conductor diameter for single core cables, right, and operating voltage is 33 kV, it is line to line and 3 phase, and maximum stress is 35 kilovolt per centimeter, and you have to find out also the radial thickness of insulation. So, it will be how we will solve it. So, look at this one only, this side do not see, this is another problem, no need to see to this side, you please see this one, the black one, black ink. For most economical condition, we know R is equal to 2.718, capital R is equal to 2.718 small r. This is equation 12, right. Actually, it is E, right. That means, ln R upon R is equal to 1. Actually, it is I am writing here actually capital R is equal to E into small r, right. So, that is why it is ln capital R for small r is equal to 1. Now, using equation 9 is your V upon, that is the maximum electric stress, it is given 35 kV per centimeter. So, formula no need to write here, I mean it is E max is equal to actually E max is equal to, it is V, that is line to neutral voltage, R ln capital R by small r, and this E max actually given 35 kV per centimeter, and line to line voltage is given V is equal to line to neutral, that is why it is line to line voltage is 33 kV. So, line to phase is 33 by root 3 kV. So, this is your V, right. Therefore, 33 upon root 3, then R into ln R upon R is equal to 35. Now, your if you solve this your ln R upon R actually 1, this is 1, because when R is equal to, it is actually ER, I told you, I have written E is equal to 2.718 say. So, ln R upon R is 1. So, from which you will get R is equal to 0.544 centimeter. Therefore, capital R is equal to 2.718 R. So, R is 0.544. So, multiply this one, it will be capital R will be equal to 1.479 centimeter. Therefore, thickness of the insulation will be, this is the capital R, right, that 1.479, and it is the diameter of the conductor. So, insulation thickness is 1.479 minus 0.544. So, 0.935 centimeter, I mean it is like this. This is the conductor, right, it is its radius, right, this is R, and this is your outer radius, this is capital R. So, this is the thickness of the insulation, this R is 0.544 and this capital R is your 1.479. So, thickness is capital R minus small r. So, that is why it is 1.479 minus 0.544. So, 0.935 centimeter, right. This is example 2, understandable, right, easy one. Example 3, in this case you find the maximum working voltage of a single core cable having two insulating materials A and B. I mean A is one insulating material and B is another insulating materials. Conductor radius is given 0.5 centimeter. Inside radius is 2.5 centimeter. Maximum potential gradient of insulation A, I am just written A, of insulation A 60 kilovolt per centimeter, and for cable B, sorry, insulation B rather, insulation B 50 kilovolt per centimeter. For insulating material A, it is given epsilon A is equal to 4, and for insulating material B, epsilon b permittivity, that is 2.5. These are the parameter given. You have to find out maximum working voltage. Now, that R your is given conductor radius 0.5 centimeter and inside radius is 2.5, that is capital R is equal to 2.5 centimeter, right, and you have two insulating materials A and B. Therefore, let the first dielectric layer A, that is for insulating material A, be up to radius R1, and between radii R1 and R is the layer of dielectric B. That means, it is something like this, just hold on. That means, you have this is your conductor, it may not be symmetrical, but this is your insulating material A, right, and this is insulating material B. So, this radius is given, suppose if it is R, right, and this is your R1, right, and this is your what you call capital R. So, this is insulating material A, this is insulating material B, his permittivity is epsilon A, his permittivity is epsilon B, and this is the conductor radius R. This is the diagram. So, that means, so let the first dielectric layer A be up to radius R1. So, it is A up to radius R1 and that and your what you call, and between radii R1 and R. So, R1 and capital R, this is your the layer of dielectric B. Therefore, electric intensity you can write Q upon 2 pi epsilon 0 is common everywhere. So, Q upon epsilon 0 into epsilon A into R is equal to 60, because it is given maximal potential gradient for insulating A is 60 kilovolt per centimeter square. Therefore, Q upon 2 pi epsilon 0 epsilon A R, right, is equal to your 60, and second one that means Q upon 2 pi epsilon 0, right, because all parameters are given, right, R is given, directly you can substitute and you could calculate you Q, because epsilon A is given, R is also known. If you put it, you will get Q upon 2 pi epsilon 0 is equal to 120. This will get it. I am not showing it here, but you can put and you can check. Similarly, for the second one, Q upon 2 pi epsilon 0 epsilon B R 1 is equal to 50, because this is 50 kilovolt per centimeter, right, and epsilon B is equal to 2.5. You put epsilon B 2.5, right, and your what you call, and Q by 2 pi epsilon 0 is 120. Here you substitute Q by 2 pi 0 is equal to Q by 2 pi epsilon 0 is equal to 120. You substitute here, then epsilon B is equal to 2.5, that you substitute here, and then only R 1 will be left is equal to 50. Solve for R 1, you will get R 1 is equal to 0.96 centimeter, right. This is a simple thing, that is why I did not write the step, but I am telling you how to do it. This value substitute here, this is 120, actually it will become 120 upon epsilon B is 2.5. So, it will be basically your what you call that 120 upon 2.5. So, roughly it will be 80 upon R 1, right. So, that way then you calculate your what you call that R 1, right, it is given is equal, this one is equal to 50, right. So, this way your you can get R 1 is equal to 0.96 centimeter. So, similarly, your therefore, voltage V is equal to, we have seen that previously for general formula. So, V will be Q upon 2 pi epsilon 0 epsilon A ln R 1 upon R plus Q upon 2 pi epsilon 0 epsilon B ln capital R by R 1, right. So, all these values are known. We have got all these value 120 by 4 ln, then this is 0.96 upon 0.5, because R 1 we have got 0.96, right, R 1 we have got 0.96 centimeter, right. So, then this one your what you call plus q by 2 pi epsilon 0 120 divided by 2.5, because epsilon be 2.5, here also q upon 2 pi epsilon 0 120 epsilon a 4, then ln 2.5 upon 0.96. So, V is coming 65.51 kV, right. This is the voltage. Now, a small question to again you, V is it a line to line voltage or it is a line to neutral voltage? This is a question to you. When you will read this, you see whether it is a line to line or line to your neutral, that is phase voltage or line voltage. This is a question to you, right. Now, example 4. So, a single core cable for 66 kV, whenever nothing will be mentioned, this is 66 will be, this voltage will always will be line to line, right. 3 phase system has a conductor of 2 centimeter diameter and sheath of inside diameter is 5.3 centimeter. It is required to have 2 intersheaths, so the stress varies between the same maximum and minimum values in 3 layers of dielectrics. So, find the positions of intersheath, maximum and minimum stress and voltages of the intersheath. Also find the maximum and minimum stress if the intersheath are not used. I mean, one, what will be the voltage distribution with intersheath, and another thing is if voltage or what you call, if intersheath is not there, what will be the your maximum stress, right, and what is the stress when with intersheath. Now, this is the problem, this is the problem. Now, referring to figure 7, peak value of per phase voltage, look, this is first, forget about root 2, first 66 by root 3 is the your whatever will come line to your neutral, that is phase RMS voltage, then multiply by this root 2, it will be peak voltage, right. That is why V is equal to 66 upon root 3 into root 2, that is 53.8 kV. Now, given that R is equal to smaller diameter 2 centimeter, so radius 1 centimeter and capital R is given 2.65 centimeter. Since maximum and minimum stresses are the same, right, all that means all are same, that means this condition holds, this we have seen. Therefore, R small r 1 upon R divide is equal to R 2 upon R 1 is equal to capital R upon R 2 is equal to alpha. Now, then therefore, capital R upon small r is equal to alpha q. Why? Because R 1 upon R is equal to alpha, R 2 upon R 1 is also alpha, R upon R 2 is also alpha, multiply all R 1 upon R into R 2 upon R 1 into R upon R is equal to alpha cube, right. That means, R 2 will be cancelled, R 1 will be cancelled, then capital then what will be left, capital R upon small r, this one and this one will be left out. So, capital R upon small r is equal to alpha cube. Therefore, capital R upon small r is equal to alpha cube, that means alpha cube is equal to 2.65 upon 1, hence alpha you will get 1 point, the ratio 1.384. So, this alpha is equal to 1.384. So, radio of intersheath are now R 1 is equal to, from this formula, R 1 is equal to alpha r. So, alpha is 1.384, R is 1. So, 1.384 into 1 is equal to 1.384 centimeter. Similarly, R 2 is equal to alpha R 1, R 2 is equal to here alpha R 1. Therefore, alpha is equal to 1.384, R 1 is also 1.384, it will be 1.915 centimeter, right. In the calculations, if you find any error or any mistake, right, calculation error anything, please your what you call, please let me know this, right. So, therefore, from equation 25, this equation V minus V 1 upon R ln alpha is equal to V 1 minus V 2 divided by R 1 ln alpha is equal to your V upon R 2 ln alpha. So, V minus V 1, R is 1 into ln alpha we got 1.384. So, ln 1.384 is equal to V 1 minus V 2, that your R 1 is 1.384, ln 1.384 is equal to V 2 upon R 2 is 1.915 we have got ln 1.384, right. Now, these equations are given. So, solve, this is 3 equation actually, this one is equal to this one equation, this one is equal to this one another equation, and this one is equal to this one another equation. So, from these 3 equations and 3 unknown, if you solve it, you will get this thing, I mean V is already given, because V actually it is known, V is given, V is actually 53.8 kV, just 2 equations. So, substitute V and you just solve for V 1 and V 2 from any two equations, right. The substitute here V is equal to 53.8, then you solve for V 1 and V 2. So, you will get V 1 is equal to 41.3 kV, this is peak value, because this one we have taken peak value, because it has been asked, right. Similarly, V 2 is equal to 23.94 kV peak value. You have to be little bit cautious about this. Read the problem carefully and accordingly you have to do. Therefore, E max will be V minus V 1 upon R ln alpha. So, it will be V is 53.8 and V 1 is the 41.3, because it is near the surface of the conductor. So, it will be 53.8 minus 41.3 divided by R is 1 ln 1.384. So, it is coming 38.46 your kilovolt per centimeter. Similarly, E mean will be when R is equal to R 1. So, it will be V minus V 1 upon R 1 ln alpha. So, 53.8 minus your 41.3 divided by R 1 is 1.384 ln 1.384, that will be your 27.79 kilovolt per centimeter, right. That means, the maximum trace. So, we got E max and E min. So, maximum trace without this is your when interseeth is used 38.46 and 27.79, this is max, this is mean. When interseeth is not used, maximum trace is at the surface of the conductor, right. That means, it will be 53.8 V is given divided by R ln capital R upon R. You substitute all the values, you will get 55.2 kV per centimeter. So, without interseeth max is very high here compared to this one. Similarly, minimum stress will be at the surface when R is equal to your x is equal to capital R. So, it is 53.8 capital R upon ln R of all the data are given. So, if you substitute you will get 20.83 kilovolt per centimeter, whereas here it is 27.79 kilovolt centimeter. So, there is little bit although not, but uniform distribution not possible, but this E max E min is better here, right. So, this is your what you call that example 4. Now, example 5. Actually, so many different type of examples are giving that sometimes I feel that all the theories whatever we make it, it should be supported by good examples. So, example 5, a single core cable has a conductor radius r and inside sheath radius capital R. The operating voltage is V. It is provided with an intersheath at radius r 1 such that maximum and minimum electric stresses in the two portions of dielectric are the same, right. Then A, find radius r 1 and voltage V 1 of the intersheath. Then B, find the ratio of maximum electric stress with and without intersheath. C, if R is equal to 1 centimeter, capital R is equal to 3 centimeter, V is equal to 60 kV, in bracket it is given RMS value, find the value of R 1, V 1 and the ratio of maximum electric stress with and without intersheath. This is the problem, right. So, how one can do this? Same philosophy we will use, there it is using I think 2 intersheath, right, so provided with one intersheath, an intersheath of radius r 1, right. So, question is that solution will be something like this: for the same maximum and minimum value of electric stresses in the two layers of dielectric, if the same maximum and minimum, then same condition will use r 1 upon r is equal to r upon r 1 is equal to alpha. Therefore, capital R upon small r is equal to alpha square, because r 1 upon r is alpha, right, and r upon r 1 alpha you multiply, then you will get r 1 r will cancel, capital R by r since alpha square. Therefore, alpha is equal to capital R upon small r to the power half, that is under root, right. So, radius of intersheath r 1 is equal to r alpha. Now, we know same formula we will use V minus V 1 upon r ln alpha, here only one intersheath is there, that is why is equal to V 1 upon r 1 ln alpha, right. Therefore, V minus V 1 upon r is equal to V 1 upon r 1, because ln alpha both side will be cancelled, right. Therefore, V minus V 1 upon R is equal to V 1 upon R 1. Therefore, V minus V 1 is equal to, right, V minus V 1 is equal to V 1, and this R, it is going R upon R 1, but V 1 we are writing divided by R 1 upon R, and R 1 upon R is alpha. So, we are making in terms of V 1 upon alpha, right. So, actually it is like this, just for your this thing, it is like this, that your V minus V 1 then from this equation is equal to your R by R 1 into V, that one you can write V upon R 1 by R, that one you can write V upon alpha, right. So, that is why you are writing, sorry, V 1 it is V 1. So, it is V 1 upon alpha, that is why you are writing this one, right. Therefore, V 1 is equal to your, just hold on, therefore, V 1 V minus V 1 is equal to V 1 upon alpha, from this two only, V minus V 1 is equal to V 1 upon alpha, from that you can write V 1 is equal to V into alpha upon alpha plus alpha 1, right. This you can, first condition you have to derive. So, this is alpha V into alpha upon alpha, your alpha plus 1. So, this is in terms of alpha. Now, second one is that your, when interseeth is used, maximum electric stress is V 1 upon R 1 ln alpha is equal to your V 1 is equal to, this is your maximum electric stress, actually V 1 upon R 1 ln alpha. Therefore, we have got V 1 is equal to V alpha upon alpha plus 1. So, this V 1 you substitute here, that is V into alpha upon alpha plus 1, then R ln alpha, and we know that R 1 is equal to R alpha is equal to, we can get V upon your what you call R, in bracket it is alpha plus 1, then ln alpha. You simplify, R 1 is, use this condition, R 1 is equal to R alpha here, and then you will find alpha will be cancelled, and it will be V upon R into alpha plus 1 ln alpha. Now, when interseeth is not used, maximum electric stress will be at the surface of the conductor, that is V upon R, R is the radius of the conductor, ln capital R upon small r, right. But we have seen R upon R is equal to alpha square, R upon R is alpha square. So, here you substitute R upon R is equal to alpha square. Therefore, it will be V upon, then this 2 will come out, V upon 2 R ln alpha, right. Therefore, ratio will be maximum electric stress with interseeth and maximum electric stress without interseeth. So, maximum electric stress with interseeth is this one, V upon R alpha plus 1 ln alpha, I mean this one, and without when interseeth is not used, without interseeth it is V upon 2 R ln alpha. So, divide it. So, if you divide V means your what you call V will go to the denominator and it will come to the numerator, right. So, it will be 2 R ln alpha upon V, V will be cancelled, ln alpha will be cancelled. So, finally, R will be cancelled, finally, it will be 2 upon 1 plus alpha, this is the ratio, right. Now, last part C it is given, I hope you have understood this. Now, if C is given, in C R is given, capital R is 3 centimeter and small r is 1 centimeter, right. Therefore, alpha square is equal to capital R upon small r is equal to 3 by 1, therefore, alpha is equal to 1.732. Therefore, R 1 is equal to R alpha, this relationship we know from here only, this condition always known, R 1 upon R is equal to R upon R 1 is equal to alpha, therefore, R 1 upon R is equal to alpha. So, that means R 1 is equal to alpha r, alpha is 1.732 into R is 1. So, 1.732 centimeter, that is R 1, right, and your V 1 is equal to V 1, just hold on, V 1 is equal to your V into alpha upon 1 plus alpha. So, V is 60 is given, right. If it is given RMS value, find out in RMS, if it is given peak value, find out in peak value, right. Your 60 into alpha is 1.732 divided by 1 plus 1.732. So, it is 38.04 kV. Therefore, ratio is equal to, we have seen earlier, ratio is equal to 2 upon 1 plus alpha. So, 2 upon 1 plus 1.732 is equal to whatever it comes is equal to 0.732. So, this is the answer, right. So, next one is this another example we will take, right. So, example 6, right. In this case a 33 kV 3 phase underground feeder 3.4 kilometer long uses 3 single core cable. Each cable has a conductor diameter 2.5 centimeter and the radial thickness of insulation is 0.6 centimeter. The relative permittivity of dielectric is given 3.1. Find A capacitance of the cable per phase, B charging current per phase, then C your charging kVAR, right. It is no need to write 2, it is charging kVAR, right. You have to find out charging current, then kilovar. Then D dielectric loss per phase if the power factor of unloaded cable is 0.03, right. So, that is this thing, and E maximum stress in the cable. So, these 5 things you have to determine. So, how we will do this? All the parameters or data whatever is given. Now, question is that R is your diameter of the conductor is given 2.5 centimeter. So, R is 1.25 centimeter. So, capital R will be thickness, this thing is your insulation is there, right. Your thickness of insulation is 0.6 centimeter. So, radius plus the thickness of insulation will be capital R. So, R is equal to small r plus insulation thickness. So, smaller is 1.25 centimeter and thickness of insulation is 0.6. So, 1.25 plus 0.6. So, that is 1.85 centimeter and relative permittivity is given 3.1. Now, from equation 7, that is C is equal to rewriting equation 2 pi epsilon 0 epsilon r ln capital R by small r, the capacitance. This same capacitance chapter for transmission system also we have seen, right. So, but 2 pi epsilon 0 is 8.854 into 10 to the power minus 12 farad per meter, we know that. Epsilon r is 3.1, capital R is 1.85, small r is 1.25. Therefore, C actually is equal to 439.7 into 10 to the power minus 12 farad per meter, but length of the cable is 3.4 kilometer. So, 3.4 into 1000. So, this is meter, right. Therefore, C will be this much of farad, right. So, 439.7 into 10 to the power minus 12 into 3.4 into 1000, because 3.4 kilometer length. So, multiply by 1000 it will be meter. Therefore, C will be 1.495. If you simplify, it will be microfarad per phase. I have written as in microfarad, right. So, whatever it is, then charging current is omega C into V. So, it is at 50 hertz. So, omega is 2 pi f, then C is 1.495 into 10 to the power minus 5, that we have computed here, and your what you call that line to line voltage is 33. So, line to neutral voltage 33 by root 3. So, and this is in terms of volt. So, that is why kV, that is why it is meant volt. So, into 1000, that is 10 to the power 3. So, this actually become 8.95 ampere. So, charging current is 8.95 ampere, right. Now, this total charging kVAR for 3 phases, as 3 phases are there. So, this is 3 is multiplied, then we have taken line to neutral voltage, phase voltage. So, 33 by root 3 per phase we are getting multiplied by 3, because this charging current also given, this capacitor is per microfarad per phase. So, charging current also 8.95 ampere. So, 33 by root 3, this is in volt, because 33 kV into 1000, that is 10 to the power 3 by root 3 into 8.95. So, it comes about 511.5 kilovar, that is the total charging your what you call charging var, quite high, right, not low. 511 kilovar means it is 0.5 megavar, right. Now, in the part B it is given cos phi is equal to 0.03. that means phi will become 88.28 degree. Therefore, delta is equal to 90 degree minus phi. So, delta will be 90 minus 88.28 because 88/2, so 1.72 degree. So, loss angle delta is 1.72 degree. Now, dielectric loss per phase in from equation 13 only we are writing omega c v square sin delta, right, that is 2 pi into 50 into 1.495 into 10 to the minus 6, that is the capacitance value we got microfarad per phase, right. 2 pi this into this it is kilovolts, we have made volt, it is v square. So, 33,000 by root 3 whole square into sine of 1.72 degree. It comes actually your 5114.6 watt is equal to 5.114 kilowatt, right. So, this is your what you call the dielectric loss. Now, last part E. E actually is given that your E max is equal to V upon R ln capital R upon small r. This is equation 9. So, V it is 33 upon root 3 line to neutral voltage, that is 1.25, that is R ln 1.85, capital R is 1.85 data given, divided by 1.2, it comes around 38.88 kV per centimeter. This is RMS value, this is RMS value, right. So, E max will be 38 kilovolt. So, these are the numericals, right. I have considered for this thing. Only thing is that if any calculation anything is wrong or anything, then you please let me know, then I can rectify myself. Thank you, we will be back again.